Welcome to Hailey Public Library in Town Center West, everyone. Thanks for coming. This is a great turnout. Thank you. And also, I just want to welcome our live stream audience who's watching from home or wherever they might be most comfortable. My name is Lynn Druin. I'm the library director, and Denon Strope is our library ops manager, and they see everything behind the scenes. So that's the big job that Denon's got going on. Tonight, we are pleased to host Dr. Rachel Smith's presentation, From New Stars to the Edge of the Universe, the Search for Extraterrestrial Life and Our Cosmic Origins, through a partnership with Boise State University, Idaho Dark Sky Alliance, and the Sawtooth Botanical Garden. Before we get started, if you haven't silenced your phones, please do so. We've got restrooms back there through that hallway. If anyone needs to do that during the show, we'll shut off all the lights here in a second. And then tonight we'll also take questions from the audience, but we'll do that at the end. So if you will please wait for the microphone so that we can be sure to share those questions with the live stream audience. And then once this event is done, the stargazing begins at 7:30 at Sawtooth Botanical Garden, which is at 11 Gimlet Road, just off of Highway 75, where I think probably most of you know where that's at. So, okay, now it is my pleasure to introduce our speaker tonight. Coming to us all the way from the North Carolina Museum of Natural Sciences, Dr. Rachel Smith is the head of Astronomy and Astrophysics lab and is the curator of Meteorites at the museum. Dr. Smith earned her doctorate in geochemistry and astrochemistry from UCLA in 2011, and has since continued her illustrious career that has taken her all around the country. An observational astronomer, Dr. Smith utilizes some of the largest ground-based optical infrared telescopes to analyze the chemistry of materials that build our planets. In addition to her role at the museum, Dr. Smith is also a professor at both Appalachian State University and an adjunct professor at the University of North Carolina, Chapel Hill. Please join me in welcoming Dr. Rachel Smith.
Thank you. Thanks, everyone. Thank you. So we'll just have to hit the light to make it all nice and dark like space. And let's see, can you all hear me? Is this on? Okay, good. All right, I'm pretty loud anyway. Anyway, so thank you all for coming. This is so great to see all of you. And I'm going to take you on a little journey through space, talking about the search for extraterrestrial life, including some of my own work, and talk about our cosmic origins. And I'll bring in some meteorite information. I do have a meteorite you can look at and pick up gently. It's an iron, so it's super robust. So if you drop it, it's not terrible, but it did fly through space. And I'm showing you this with software called Open Space. And I did give this talk last night at Boise State, and they took almost all of my card, which is fine, about Open Space. But it is free software, so if you don't get a card, it's first come, first serve. And I'm sorry I didn't bring another bunch of these, but this just tells you a little about the software. But it's openspaceproject.com, and it's free software that I've been working on as a partner with the American Museum of Natural History in New York, and it's NASA funded. So we're in our 10th year of funding and developing programs, and it's all data driven, and everything you see here is based on actual real data. And so I'm gonna start here, and I'm only gonna be able to tell you a little bit. Open space is amazing, you can see the whole universe, but we don't have time to do the entire universe today. So this is our solar system, and you can see the Milky Way back here. All the stars, they're a little bit larger than you'd normally see, just so we could see them here in the software. But every star you see in the sky and the stars you see tonight in the sky are in our own galaxy. And we cannot see stars with our naked eye beyond our own galaxy. We have 8 planets in the solar system. Pluto's out there, but it's not a planet. And when we think about life, remember, we're the only planet with life that we know of in the entire universe, which sounds so crazy, but it's true still. And there are many reasons why that might be. But I'm going to turn some stuff on. There are all these data sets you can use with Open Space. So I'm going to first turn on what's called the habitable zone. Every star has a zone called the habitable zone. And this is this green circle here. And this is where liquid water can exist on the surface of a world. And that's the definition of a habitable world from a scientific perspective. So as you can see, Earth is here, And Earth is the only planet in the habitable zone, squarely right now in our habitable zone. But our sun is 4.5 billion years old, and at one point in time, Venus, which is too hot right now, and Mars, which is too cold, although it's sometimes put a little bit in the habitable zone because it sometimes can have a little bit of water maybe on its surface, but it's not a living world right now. But at one time, both of these planets were also in the habitable zone. So because Mars is too cold and Venus is too hot and we're just right, sometimes this is called the Goldilocks zone. Really, truly. So every star we see, every star out there will have a habitable zone. It doesn't mean that there's necessarily an Earth-like planet in there, but we're trying to understand this and build this picture. So what I'm going to do now in terms of describing our origins a little bit is first I'm going to turn this off, and well, I'm going to turn around the solar system a little bit, and you can see that the solar system has a pretty narrow, a really nice orbital plane here. It's a pretty straight plane. It's few planets deviate off. It's the plane of the protoplanetary disk that we formed from 4.5 billion years ago. And I'll show you an animation of this disk. This is a protoplanetary disk. It's a drawing, but it's a star forming surrounded by gas and dust. And my research focuses on the gas in front of forming stars that are forming today. And I'll talk a little bit about my research in a little bit. Our disk is gone. We now have the planets. But we preserve this plane of our disk by the planetary orbits. And the remnants of this disk are the asteroids and the comets. And I'm going to turn them all on. They take up a lot of bandwidth because they are very large data sets. And if you're wondering what's out there, here's some of them. Not all of them, okay? So there's a lot. This is the leftover debris from our planet's formation. And space is vast, so even though we can zoom in and say, oh my gosh, they're all over and they're going to come hit us, chances are pretty small that you're going to be hit by an asteroid. There are just so many out there, though. They're mostly between Mars and Jupiter. And if you look here, you can see these two groups of asteroids here called these are the Jupiter Trojans. They're my favorite because they show how massive Jupiter is by the fact that they're kept apart. And Jupiter is so massive it pushes apart these two groups of asteroids, and it is part of our understanding trying to figure out what makes a habitable world. And one of the factors might be a Jupiter, some kind of giant, massive planet that is able to pull in the asteroids and comets for us so they don't hit us all the time. And we certainly have been hit by asteroids, and I'll show you some modern hits. And in the past, I'm sure some of you are familiar with some of the famous hits of the past, and we will be hit again. But you don't have to worry too much about that, and I'll tell you why in a little bit. So I'm going to turn these off. Right now I'll leave on, as we go to a crater, I'm going to leave on the Mars crossers and the potentially hazardous asteroids. And these are the ones that could hit Earth, most likely. And so I'm going to just I have these bookmarks. You can bookmark things in open space. As I said, it's free. You can download it, and it's nice to have a good gaming computer to run it. And there are specs online that'll tell you what you need to run this planet. And somehow Earth is, did I turn something off on Earth? Earth looks odd. Let me go. It looks see-through, which is not what we want. So let me go back to Earth. And Earth is standard. Okay, so I must have done something. Hold on a second. This is Earth. There we go. You can turn Earth off if you're sick of Earth. Some of us might be, right? Okay. But sorry to say there's nowhere else we can go in the near future, so we have to take care of Earth. This is Meteor Crater. So this is a famous crater in Arizona. Some of you may have gone there. And Meteor Crater was formed from an asteroid that hit about 50,000 years ago. And I'll show you, some of you may have been there. Has anyone been there? It's really awesome, yeah, it's awesome. It's really well preserved, and we have been hit by as many asteroids as other planets that show their asteroids more than us. So the moon and Mercury in particular, they showcase their craters, and those craters aren't really going to go anywhere because there isn't as much weather and they are not dynamic living worlds like we have. And so in open space, you can go all over. You can go all over the Earth. It's beautiful. We have all the data we could ever want from Earth. And Mars and the moon, all the data, all the surfaces I show you, those are from, we're not going to go to the moon today in this program, but the data sets are beautiful because we have an orbiter going around the moon called the Lunar Reconnaissance Orbiter. So this crater was made 50,000 years ago when what was there were giant sloths and woolly mammoths, and I like to show them because they're so cute, and they're not there anymore. So we will be hit again, and we'll just stop here on the crater for a second, and I'll show you a few more things about hits. So this is Chelyabinsk. This was an asteroid hit in 2013. There's an actual image taken from a dash cam in Chelyabinsk, Russia. This is a chondritic rocky meteorite that smashed through the atmosphere. It wasn't very big. It was about 30 meters across. But it was enough to cause a lot of damage, and a lot of people were afraid because they thought they were being attacked. And the amount of energy in an asteroid hit, even one small like this, even a small fireball, is many times more than a nuclear bomb. And the reason they don't feel those effects as dramatically as a nuclear bomb is because those explode. The the meteoroid will explode in the atmosphere versus on the ground. But space delivers way more chaos than we can even do ourselves, if you can believe it. So this happened in Chelyabinsk, Russia, and the most famous probably hit was in the Yucatan 65 million years ago. This is Chicxulub, and this is the Yucatan Peninsula in Mexico. And what happened then? The extinction of the dinosaurs. So I show this. You can find some imagined sketches of what this might have been. This is a very dramatic, probably inaccurate emphasis because rock wouldn't come smashing in like that, and those poor flying reptiles wouldn't have a good day. And because of this impact, the dinosaurs were on their way out. They were absolutely went extinct because of this over several years. And then the mammals became prominent, and that's what we are. So extinctions from asteroid impacts have definitely influenced the evolution of life. And we try to understand this as well in terms of how do we search for life? What type of life might we find? That's a big question. So in astrobiology, we learn about our own planet as well as other worlds. So it does have, we are learning about ourselves as well when we study space. This is a piece of a meteorite from Chelyabinsk. So a meteorite is the piece of the asteroid that actually you can pick up. So once it lands and you pick it up, that's a meteorite. And this is a rocky meteorite that you can see this beautiful crust. And this is called a fusion crust. So when meteorites fall, and you may see them here, shooting stars, and if you ever pick up a meteorite that's fresh, it should have this crust. And that is a more pristine sample that people really want. They're kind of remnants of their fall. So I bought this one in Russia when we were there for a meeting, and I was able to buy this, and it's a really nice sample. I like the crust, and it's in our collection at the museum. This is another meteorite that I like to talk about. This is our sample of Tarda. This is a meteorite that fell in Morocco in 2020, and it has amino acids. And amino acids are complex molecules that all life, every single bit of life on Earth uses. All life uses the same 20 amino acids. But meteorites, some meteorites, a small few, have amino acids that extend way beyond these 20. And a lot of astrobiologists are studying this to try to understand if the ingredients for life could have been delivered from space, which is quite possible. We really don't know how life started on Earth, but complex organic molecules and water could have easily been delivered from the comets and from asteroids. And so Tarda is one of those examples that has these really interesting amino acids, but it's not the first one. There are some meteorites that have well over 100, and they've been studied quite extensively, trying to understand extraterrestrial amino acids and some amino acids that are just like ours that are also in meteorites. This is a comet. This is Comet Neowise. We get delivery from comets. So comets are much farther away outside the orbit of Neptune than asteroids. This is from my yard in North Carolina, and it was Neowise a few years ago. And you can get really beautiful pictures of comets. And these are the remnants from our solar system's formation 4.5 billion years ago. So when you touch a meteorite, even one that's not as old, this is not the oldest because it's a core, it's an iron. So the rocky ones are much older. They are older than any other rock on Earth. We don't have any rocks that date as old as the meteorites of 4.5 or 4, it's actually 4.567 billion years old. So comets, asteroids, meteorites, these are the materials we can study to try to understand our origins. And the work I do with studying stars forming today, that also helps us understand our origins because they're analogs to our early solar system. So I talked a lot about meteorites, so now we're going to leave Earth. I'm sorry. Because we have to move on to space, to more planets, and we're going to go to Mars. So I'm going to take you to Mars to, oh, wait, one more, I'm sorry, I forgot this one important plot. Oops. This is the probability that you will be hit by an asteroid, so everybody wants to see this one. And what's the probability that you'll be hit by a KT, or dinosaur extinction type meteor? That happens once every 100 million years. So, but astronomers think in orders of magnitude. So for us, 65 is the same as 100. So some astronomers think we're due for another KT type asteroid. That being said, we can map out these asteroidal paths to 100 years. So in the next 100 years, there's nothing coming that's going to be an extinction or planet-destroying event. But Chelyabinsk meteor sizes happen once every 10 or 20 years, and every day we get bits of material coming in, and you can actually collect it on your rooftops. And most of it, of course, lands in the ocean. So we get delivery from space all the time, but the bigger the asteroid, the less likely it's going to come because there are fewer larger asteroids out there now. It's a very easy plot to understand. It's indirect, so bigger is less often. So there you go. All right, now we're going to go to Mars. Mars is our neighbor where we are sending plenty of probes. We have lots of data sets to show in Mars, so I'm only going to pick one place because we don't have time to go anywhere else, and that is Jezero Crater. And I like to talk about Jezero, not only because we're there now with the Perseverance rover, but because we can talk about habitability. There it is. I put these little bookmarks because I can't find my way in space yet perfectly, but I'm getting there. I'm trying. So I'll drive. So open space, you can drive. There are tutorials in how to drive with open space. I have to turn one data set off here. So let me go up to the top and turn off. So you can see what I'm doing, and I'm turning off. You can turn data sets on and off. So I like to teach my students about data sets with open space because they can learn to drive it. It's actually very easy to drive, and as I said, it's free, so even anybody can do it and drive it around. So what I'll say first is if you can see this riverbed, this is an ancient riverbed. When Mars had water, okay, so when life was kicking in about 3.5 billion years ago, or 3 billion years ago, depending on where you look, life was starting and Mars was becoming less habitable. And that's because Mars was losing its magnetic field, and the solar wind pulled off the atmosphere and all the water evaporated. But there's tons of evidence, such as Jezero, that says water was on Mars. And we really know that Mars had a lot of water. And where there's water, there could have been life. So I'll extend this up. You can see the Mars crossing asteroids right there. And I'll zoom down a little more, and we'll go into Jezero. We picked this crater and this ancient river delta to send Mars 2020, or the Perseverance rover, because there was water there. And where there's water, there could have been life, and so it's looking for past life, but there's absolutely no evidence of any life there yet. But what the rover's doing is it's also caching, so it's taking samples of rock and soil and sticking it in vials so that if we ever go to Mars for sample return, we will have some samples that were already put together by Perseverance. You may be listening to the news a while back. NASA just let go all their Mars sample return people. So who knows, based on funding, so we rely on that federal funding to explore space, and that's a thing to think about as well. But one of my favorite parts of this mission is the little drone. I keep forgetting to talk about this image. But anyway, this is the result of the Chelyabinsk impact. So it's still significant, and the first documented injuries from an asteroid impact. So sorry about that. But now we're back on Mars. This is Ingenuity. This is a little drone that's the first powered flight on another world. Very first one. Mars has a very thin atmosphere. It's like 100 times thinner than Earth. And it wasn't certain that this drone would work, but it did. And it flew for 72 flights. Highest it flew was 80 feet, and the total amount of time was a little over 2 hours. But that is a real achievement for an extraterrestrial powered flight. And I have several images of it because I think it's really awesome. You could see I like this one because it's just this little tiny thing out on this other world and exploring, and it's just amazing. It damaged its rotor, or it fell over. It didn't do it. Somebody did it, but it got somehow it fell over and damaged its blade. And they had a whole story how sad it was. It was very sad. I felt bad for it, even though it's a machine, that it was dead. And eventually, if we go back, we'll pick it up and maybe tape it back together. But that was ingenuity. And I will say that when we try to think of life on Mars, what could it have looked like? One example that's very similar to mineralogy, to what has been already determined on Mars from the orbiter, are these stromatolites. These are ancient single-celled microbial mats. This is from Australia, and this is some of the earliest life. And if there was life on Mars, the mineralogy that we understand from stromatolites, it could have been very similar to what was in Jezero Crater. And so we're trying to understand these extreme and primitive life forms on Earth and how that could influence where we search for life in space. And while we think that Mars doesn't have life now, or we're not sure, but it's unlikely, certainly unlikely on the surface, it could have been habitable in the past with something like this. And a lot of people think, well, we're going to go to Mars and we're going to terraform Mars. It's going to be the next Earth. And it's sorry to say it's not true, because we can't breathe on this planet. We have to figure out if we can terraform this planet, and that means creating a new Earth. And we have no way to do it, but this is a schematic drawing from NASA of what it could look like eventually if we get a foothold on Mars to build factories. And we're very good at building factories with greenhouse gases, and that's what you have to do for Mars, but we're not very good at controlling the greenhouse gases. So we don't even know if we can do this. And so this is just a schematic, but it's something to think about what would have to happen to not only create this atmosphere, but hold on to this atmosphere. Because right now, Mars does not have the ability, without a magnetic field, to hold on to its atmosphere. So there's a lot of work that has to be done to make a habitable Mars, and it may never be possible. It could be beyond our ability to actually get that technology together before we become uninhabitable here. So we have to think about that. But eventually, we might become someone like this, who has an ocean and can take a swim on Mars. So I really like that picture. All right, so let's go on. We're going to go now to Europa, which is a world to really talk about. And before we get there, I'm going to turn off my asteroids. They take up some bandwidth. So, all right. So those of you on the stream, I'm just going to tell you, open space sometimes doesn't look as great. It's a moon of Jupiter. Doesn't look as great on stream, but don't let that deter you from trying it out. What you're seeing streaming here in the background, these are Jupiter's moons. Jupiter has many moons. All these giant planets have 90 to 100 moons. They're very large. They capture moons. And Europa is the most exciting moon of Jupiter for astrobiology. And that's because we think it has a global ocean. Europa is smaller than our moon, but if it has this global ocean that we think it has, it would have more water than on the entirety of Earth. And with water, again, think life. And how does it keep its nice warm ocean all the way out there at Jupiter? It's because Jupiter is pulling on it constantly, and it's called tidal flexing, and it's keeping it warm. And that nice warm water, you can see it has craters too, that nice warm water under the ice is a perfect environment for possible life to start. And we think life on Earth probably started under the ocean at a hydrothermal vent type system. And so it's likely that if Europa has this ocean, it's quite possible it has vents underneath, and it could have an environment, an ecosystem with possible life. What kind of life will it be? It'll probably be, if it's there, single-celled microbial life, because life, it takes a lot for advanced life to happen. We have a mission going to Europa called Europa Clipper, and you can see these stripes. These are cracks in the ice where the ocean is coming up periodically. It's a really fascinating moon, and Europa Clipper will be going to Europa. It won't be landing. It'll be flying by Europa, by orbiting Jupiter, and it will get there around 2030. So this is a really prime target for astrobiology to search for life, again, beyond our habitable zone, but within our solar system and within our reach. So the last moon I'm going to go to is Titan. And someone asked me yesterday, they said, what about Enceladus? You didn't mention it. I will mention Enceladus, but I won't go there because we don't have time. But Enceladus and Titan are moons of Saturn. You can see beautiful Saturn out there with its beautiful rings. Also has lots of moons. And we're going to stop at Titan. Titan is, for astrobiology, there are two moons that are interesting for Saturn. There's Enceladus, which looks a little bit like Europa, but smaller. It has an ocean probably underneath as well. There have been geysers seen spewing out just like Europa. But there isn't a mission right now going there. The priority is Europa. It's closer. It has more water. But we have been to Titan, and Titan is really interesting for a couple of reasons. It's the only other body in the solar system with liquid on the surface. So we have liquid water, but it's too cold for liquid water on Titan. It's like negative 400 degrees, 200 to 400. So it has liquid methane and ethane, and these are hydrocarbons. So anytime you hear carbon, all life on Earth is carbon-based. So hydrocarbon lakes are fascinating for astrobiology, even though it's not liquid water. There are many studies being done to try to explore what kind of life could live in a hydrocarbon environment. And so there have been theoretical studies with this, and we have been to Titan before in the early 2000s, landed a probe called the Huygens probe that took some images of these areas, but not great resolution. And so there's a new mission that's being started called Dragonfly. This is, I think of it as Ingenuity 2.0, because that little helicopter on Mars helped pave the way for Dragonfly. It looks to me like the Terminator Part 2, where it's like bigger and better and shinier, even though I'm not going to say it's better because I still love Ingenuity. But it's shiny, and it's the newest, shiniest thing. And it should fly in the next decade, hopefully. And it will be a powered helicopter that's going to go all around Titan and look at these lakes. And so it's a really interesting mission. It's being led by Johns Hopkins by a woman named Zibby Turtle, and she is really amazing and leading this mission. So keep your eyes out for Dragonfly. But the other reason to go to Titan is not just for the hydrocarbon lakes, but because of its nitrogen atmosphere. It has an atmosphere much like the primordial Earth, the early Earth. So we could learn about our early Earth as well by going to Titan. So that makes it also equally fascinating. The last stop on Earth, I'm going to go back to Earth for 1 second, and we are going to, I'll just talk a little bit, I'll put Earth in the focus, and I'll talk a little bit about my research. I won't dwell too much, but I'll just bring up the fact that, we can explore astrobiology in many ways. And by looking at stars near us, we can try to understand how our star formed as well. And the best way to do that, I think, is, especially with the work I do, is with ground-based telescopes on Mauna Kea. And that's in Hawaii, and I'm going to go there here. I'll find my little area here. And I'll just talk for a little bit about that, and we'll zoom into the big island of Hawaii. This is a very beautiful place, and I'm just going to center it back on Earth. And Mauna Kea is, the big island of Hawaii is the only active island. Oh, what am I doing here? Okay, there we go. Is the only volcanically active island right now in Hawaii. And it has 13 telescopes on Mauna Kea. So here's Mauna Kea, this is Mauna Loa. Mauna Loa does erupt sometimes, and of course Kilauea down here erupts many times. And it's an amazing thing to see if you're out there to see the flowing lava. Mauna Kea is really gorgeous. It has these cinder cones you can see here. It's a shield volcano. And so there's a lot of comparative planetology done on Mauna Kea and Mars, actually, because Olympus Mons on Mars, which is the biggest volcano, planetary volcano in the solar system, is also a shield volcano. So we all form from the same stuff. And all the ingredients are out there for Earth and life, and we're just trying to find it. So we'll zoom down. This is Mauna Kea. It's 14,000 feet in elevation. The telescope I use is this little one over here called the NASA Infrared Telescope Facility. And it was built to support the Voyager mission back in the 1970s, and I'll talk about that again after I show you a little bit about observing on Mauna Kea. I have used Keck, that's right here, but right now for the work I do on looking at the gas in front of these stars, IRTF is even better because it has an instrument on it called iShell, which I need to look at spectra. So I'm going to show you a little bit about observing. So I took this picture. This is one of my recent observing runs. It's a fairly small telescope. It's about 3 meters, which by ground-based state-of-the-art observing standards isn't huge. It's big and awesome, but it's not Keck, but we don't care. We love it. And it's better in a lot of ways. Here it is up close. You go in the door. That's me in the dome. And I'll just tell you, being at the telescope, I say this all the time when I talk about observing. Being on this mountain in that telescope is the best part of my job in terms of science, because it is connecting to my data as close as I can get to my data. And as scientists, we are studying the natural world. Anything we do as a scientist is really trying to understand our natural world and even being part of our universe. And if you don't go to your instrument and go to that site, you lose some of that. And science is a creative process, and what it does to be there and be part of this setup is really awesome and amazing, and keeps you into that, you're really immersed into that science. And so I always go up there, and it's one of 2 telescopes now in Mauna Kea that they let you go up as a scientist. There are some people working up there, but they don't, it's a pain in the butt if you're a scientist and you fall over because you can't handle the elevation, or we're not used to it or whatever. So most telescopes don't want you up there, even though we're kind of the reason they exist, because we're the scientists. But anyway, so IRTF lets you go up there, and so I absolutely love doing it. And when we go up there, I am in the dome for the beginning of the night to to just watch them set up. It's usually me and this one other guy. This is where we observe. Through this window shows the office where we observe, the observing room. And this is where we cool down the telescope or the instrument, because they observe in the infrared. Heat emits in the infrared, so you want your instruments very cold. And so you cool them down with the liquid nitrogen. And the instrument I use is called ice shell, and it's right here. And I think, oh no, I didn't, that's the only slide I have of that. So this is the instrument, it's a spectrograph. So it takes spectra of carbon monoxide and other molecules, and I'm specifically looking at carbon monoxide. We open the dome to the great wide space up there on this beautiful mountain, and we observe inside here. So the telescope operator sits here, and I sit here, and I will be operating the instrument, and the telescope operator monitors the dome. He has weather cams up for all the domes up there, and it's one of the most solitary and amazing experiences that you can do, is be up on Mauna Kea in the middle of the night, surrounded by just a few people, and the emptiness of all of it, and it really feels like you're there near your stars. It's hard to describe. This is me very tired, so we'll skip that. This is a heat image. This is one of the guider images that I take throughout the night of these stars, and this is called the guider on the telescope. And the blob here, this is the hot dust around the star. So the dust emits in the infrared, and when you take pictures, which even though the pictures are not what I analyze, they're really informative. It shows the nice hot dust, and they're visuals, so I show them when I talk about my science. And so this is one of these. Inside the dust, there's all the gas as well, which is what I'm observing. These are the spectra. You can't get a talk from me without me showing you some spectra. So this is what you're going to look at for a second. Nobody at the museum, I tell them, they're like, don't show us spectra. The public doesn't say that. The people I work with, they're like, they want flashy planets. But I tell them, this is the science, and they're starting to learn to love spectra like I do. So these lines coming down are the fingerprints of carbon monoxide. This is some of the best data we have of these stars. Each rectangle is a forming star, and each one gets analyzed, and I zoom in and I analyze the lines. This is how we study the CO of these forming planetary systems. And the CO will go into planets eventually, because we think every star should have planets, and the molecules needed for life. Before they become spectra, when the light comes through the telescope, you get a picture on a CCD, like a camera. And then you go home and you stack up all these pictures and run them through a pipeline of codes to get the spectra. But I show this because this is actually what the data is that we take home with us. And these 2 lines here, if you look carefully, you see 2 kind of train tracks. This is a binary system, 2 stars forming together. It's the most common architecture in the galaxy that we know now, but way back when, we didn't know that. And this is just some spectra from that binary. But way back in the 1970s, when we had Star Wars, this was science fiction. So binary was part of this fanciful universe made by George Lucas, but now we know that binaries are the most common. And so I love talking about this, because not only is that binary system my favorite to analyze, because it's got beautiful lines and it's very interesting for lots of reasons, but it's an example of how science and science fiction sometimes meet up. And this is obviously is Tatooine, but we know that binaries are out there, and they're the most common. So the work we do with binaries is really informative for lots of types of stars. Okay, so now we're going to leave Earth. I'm going to refocus on, let's see, we're going to refocus, we're going to go zoom out, and what I'm going to do is before I zoom out, I'm going to turn on the exoplanets, and these are the actual planets we know about, right, that we've observed. And each circle and each dot is a data set that we know of. I'm going to actually refocus on the sun here, our center, is a data set. And so there are about 5,000 or so known exoplanetary systems. And I'm going to zoom out. You see our solar system is disappearing. And as I zoom out, I'm also going to turn on what's called the radiosphere. And this is for astrobiology, for SETI, for the search for extraterrestrial intelligence. We think about the radiosphere. And this is the sphere of extent for our signals to space. So let's stop here. In the center of this hypothetical sphere is the sun and the Earth. We've been sending signals out to space for about 100 years from radio and TV, and we're now kind of going dark because we're going digital. This is as far as we've sent signals to space. Okay, so for SETI, who understood this is Carl Sagan, and he was a big proponent of SETI, and especially with Voyager. And the Voyager mission, which the infrared telescope facility, which I use now for science, for my science, was used to support this mission, was to take pictures of the giant planets. And one very famous picture that Sagan took as he's thinking about life beyond our world and how we see ourselves as the only habitable world in the solar system was this picture. And some of you may know about this one. It's from his famous pale blue dot speech. This is Earth right here, this little white dot. And this is Earth in a sunbeam of light. That is the first time anyone saw Earth like this. And it really brought into these ideas of environmentalism and how do we think about our planet. How does this affect our lives to know that Earth is really this tiny pixel in a sunbeam, is how he described it. And he talks about in the pale blue dot, no one's coming to save us, and nothing is out there that we know of, even though there are exoplanets out there. And the first exoplanet was discovered in 1992, 4 years before Carl Sagan died. But he was a big proponent of SETI, and he said, if we're going to send these missions out there, these probes, we need to make sure we include something from us. And he put on each mission, each probe, the golden record. So each Voyager probe has a golden record with directions on how to play it for some extraterrestrial that may or may not be there. And if they were going to find it, he said, we probably won't even be here. So it's a way to think about the importance of making sure that everybody who's out there, anybody, any life, knows they're not alone. And it's part of all the work we do. Are we alone? And nobody has this answer, but all of the work we do as scientists is trying to get at this question. So my work is trying to understand, are there other habitable worlds, and what kind of chemistry do we have in other star systems to make a new Earth? And then there are people listening for aliens possibly, and that's very hard to do because we don't know where to listen. But he says we need to put these records on with directions, with sights and sounds of Earth. So I encourage you to go to the website of the Golden Record, and if you Google Golden Record, you'll find it. And you can download all the sights and sounds of Earth and languages that they put on this record so that some aliens could find it millions, billions of years from now. Okay, so let's think about this radio. So we have not heard from any of these planets, okay? Nobody sent us a signal so far. This is the extent of our planets that we've observed. And we're going to see this in the context of our galaxy. This is our galaxy. We have an image of the galaxy, so we're in the galaxy. This is partly an illustration. We don't have a full image of it, so it's an illustration as well as some imagery. This is us inside our tiny, tiny radiosphere in this dot, and surrounded, these are all the exoplanets we've ever observed. We think that there are probably billions of exoplanets. That would make sense scientifically. We just haven't seen them yet. And we've heard it from nobody. There's no sign of life anywhere else. It is 100,000 years from one end of our galaxy to the other. 100,000 light years, sorry. 100,000 light years, meaning it would take light 100,000 years to go from one end to the other. And we travel at 0.0005% the speed of light. So we're not going anywhere, I hate to say. We got to decide what we want to do here. So it's, we're not going anywhere. But let's say we are one of hundreds of billions of stars in our galaxy. Okay, one of hundreds of billions. Each dot you see here, past the galaxy, is another galaxy with hundreds of billions of stars. So the idea that we're alone is very hard to believe, right? That there's so much out there. Each of these dots has hundreds of billions of stars, and they could have billions of planets as well. And so let's zoom out some more, and we see galaxy clusters, and each cluster has hundreds of billions of stars and galaxies. And so we have a universe full of potential. And this is the Planck data set, where you can see all of the galaxy clusters we could possibly find. And then we're going to keep going to the cosmic microwave background. This is as far as we can see of the universe. It is 13.8 billion light years away. This is the heat left over from the Big Bang. So our solar system is only 4.5 billion years old. The universe is 13.8 billion years old. So if there's life out there, that life will likely be much more advanced than us. And that's what has inspired SETI and inspired films. Now, I think, of course, these are famous films, you may know some of them, When the Earth Stood Still and Close Encounters, and plenty of others that we have all grown up with this idea that extraterrestrials are out there. They often look very much like us, which is completely a construct of our imagination, and that we've been visited. But these kinds of stories we've told are filling in the gaps in our knowledge, which is what we do as humans, what we have in the library, right? Is we love stories, and we do this to try to understand our place in our natural world. And so this science fiction has inspired scientists and has also kept people interested in space. And some of you may even be here because of your interest in SETI. Sagan and Drake really tried to put an objective spin on this and say, let's come up with an equation that could give us some idea of how many intelligent civilizations could be in the galaxy. And the definition of intelligence in this case is communicating off your planet with a telescope. Otherwise, you can't hear them. So there could be planets full of, dolphins or parrots or something that don't communicate with telescopes. We'd never hear from them. So for SETI, we have to think of advanced civilizations. And remember, we're very young. So if they're advanced and they survive themselves, they'd be much more advanced than us. So I'll talk a little bit about this equation. N is the number, how many intelligent civilizations are out there. And we can get a handle on some of these parameters. So R is star formation rate, and we have a number for that. We astronomers are pretty good at figuring that out, so we have a number for this. How many stars have planets? What fraction of stars have planets? We think every star should have at least one planet. How many of these planets are Earth-like? Well, we can come up with a number for that. There's theories and models for that. So how many numbers of these are Earth-like? That's a number we can figure out. How many of these planets have life? That's a number we'd have to back out maybe from our own solar system, maybe 1 in 8. Who knows? We could just say an eighth, because we have no other example, or there are theoretical models out there that take in consideration habitable zones, and you could come up with some reasonable estimation for F sub L. Now, these last three, nobody knows. How many of these life forms are intelligent? What fraction? What fraction have civilizations? And how long do they live? And this is the ominous number here. Can we survive ourselves? Can intelligent life not destroy themselves with bombs? And the technology that it takes to get to space is also used for nuclear bombs and other things, and climate change and everything else. L is longevity. And it's quite possible L is very low. And that may be why we don't hear from these planetary systems. It could also be that they're just so far away, which is what Carl Sagan would say. And I believe that. Personally, what resonates with me is that the planets are so far and space is so vast. He said space is vast and the stars are far apart. It's very hard to wrap our heads around this number when we are in a very human time scale day to day. But 100,000 light years is the extent of our own single galaxy. And then you have empty space for most of space, and then other galaxies. So we have no way to travel between these worlds. So if we come up with a reasonable number, not too big, not too small, 10,000, say there are 10,000 Earth-like worlds with civilizations, hearing talks like this one, hoping it'll end. All of this, coming up with a number, say it's 10,000. The nearest would be 900 light years away. And that means it would take 900 years for a light signal to get to them at the speed of light. And then 900 years to hear back from them. So maybe there's something out there 900 light years away that hasn't heard from us yet, and then we would have to wait for a signal to come back. So that maybe helps think about these vast distances. Nevertheless, even when scientists put these numbers together, people want to think about science fiction and want to have more to think about. So this guy, Nikolai Kardashev, came up with a way to think about, well, how could you scale civilizations based on their energy use? So the first type is planetary, and that is a sustainable use of your planet. So we're not there yet. We're like type 0.3 or something, depending on where you read, sustainable use of your planet, that we could maybe get there in a few hundred years, some studies say. Type 2 is stellar, where if you maybe heard of a Dyson sphere, this is where civilization could wrap their star or stars with a sphere that harnesses all the energy from their star. And then the infrared energy that's emitted, the waste heat from that shell, could be observed. And there are some papers about this, some reasonable science papers about how you might know you're observing a Dyson sphere. The last is type 3 is galactic. That's like Star Wars zipping around at light speed. And we have no evidence for a galactic civilization. But it's not unreasonable to think this could exist at some point in time. And so this is where you can try to get an objective thinking about these civilizations and what they could be like. But yet what we might think of are these things. Roswell, there are so many theories and conspiracy theories and sightings, and all these aliens that we've grown up with look a lot like us. Maybe not exactly, hopefully, but it is kind of cute. They look a little like my geckos, but I have geckos. Maybe because I like aliens that I have geckos. But they look like this, and this is all comes from, all of our depictions of science fiction come from where we are culturally. So like Twilight Zone and abductions and loss of bodily autonomy and all of the fears and stuff with the Cold War that all came up in the 60s and then resurrected these ideas of government conspiracies that persist today with UFOs and all these things you've been hearing about. So the alien idea still exists, and in spite of all the evidence to say we have no proof that there's any aliens or any UFOs that are extraterrestrial. Okay, so I think I pretty much covered what I wanted to, and I wanted to just zoom back and take another, we'll go back to Earth and maybe get this perspective, and I can take your questions, and you can also take a look at this meteorite, and we'll go back to our home, our galaxy, and you have maybe some new ideas about life on this planet and life elsewhere. But I'll just leave this and I'll let it rotate around and I will take your questions. So thank you. And you can turn the lights on, that's okay. So I could take your questions. Who has a question? Yeah.
With radio telescopes exploring potential signals coming from all over the universe, how does that process work? How specifically do they have to focus? Can they take in a whole wedge of space? Do they have to focus at a particular point? How slow a process is this, and how long is it going to take to get a whole bunch of potential signals coming?
Great question. So I don't know the triangle of precision for these exactly, but a radio dish are these big, big radio dishes. And this is just one of the interferometers that are in California for SETI. My understanding is they point to a pretty wide range. And so one of the reasons to make an inventory of these exoplanets is where should we point? Where should we listen? And I don't think they I don't think they have the precision of a single planetary system. I mean, you certainly can try to hear these signals, but that's a really good question about what the width of the signal is. How long it'll take is anybody's guess, but that's a great question about, I'm pretty sure it's very wide. And if they get a signal, it's going to come in from a very wide region and then they can hone in on it possibly. But remember that these signals also dissipate through space. So if something is sending indirect, like if we send signals out to space indirectly, not intentionally, like saying continuously, hello, we're here, hello, hello, like a laser, these radio signals and TV signals are going to get weaker as the square of the distance. So any signal that's coming indirect, just happens to be like waste signals from these planets is going to be very weak. So I don't even know if we'll hear it. And so that's a good question about that. I'm not sure, but I think it's a pretty wide range of radius that they get. Yeah. Sorry, you could I'll let you decide. I'll let you decide. Just like when I pointed over there, nobody knows who.
Okay, you're saying that our solar system is flat and our galaxy is flat. So is everything flat, and are they just like sandwiches?
No,
next to each other?
So the universe is flat, even though our observable universe is a sphere. So the universe has been measured. It's not appreciated in open space, but the universe is actually a flat sheet. But our observable universe, meaning it's dependent on where you are. So our observable universe is like a celestial sphere, and it's a sphere around wherever you are. So we see a spherical thing, but the universe is actually flat. That's been measured by missions, that it's a flat sheet, and it's accelerating into nothing that can be defined. And so the plane of the solar system is relatively flat because that's the plane of our protoplanetary disk. So that's what I was meaning by that. So it is a flat plane, but it's not flat in maybe the way we're thinking. But each object is spherical. But the plane of the orbits of the planets is flat, is a flat plane, basically, with a little bit of degree wiggle. That's just the orbital plane. I don't know if that answered your question. Did it kind of? I mean, think about when we observe out, we observe a sphere, but that's not the shape of the universe. The shape of the universe is a flat sheet, but you have to measure that elsewhere with a different mission. So it's a little bit confusing.
I just had kind of a social question. Is SETI an international cooperation organization?
I don't know of any international groups doing it. SETI is, science is international, so there are scientists who are hired at SETI to do work on astrobiology. Not all of them. The SETI Institute hires scientists on soft money, so they raise their grant money. Some of them listen for signals, and Jill Tarter, who is the inspiration for Contact, for the book Contact that Carl Sagan wrote and the movie, she's still there as a kind of one of the directors. But the listening, I don't know what percentage of them actually listen, and I don't know of any radio telescopes. There was Arecibo that fell apart, and that was in Puerto Rico. But the radio dishes that I know of are these in California and also Green Bank in West Virginia. I don't know of other radio, in ALMA in the Atacama Large Millimeter Submillimeter Array in Chile. That's used for actual imaging of protoplanetary disks and other science. I don't know of any use of SETI for that telescope. So I'm not sure if ESO, which is the European Space Observatory, is really doing anything with SETI. That's a good question.
I assume that since the Dyson sphere, in steady state would be radiating the amount of energy the sun is putting out, and that's going to be in the IR region. Is the Webb telescope a good tool to look for Dyson spheres, and do we have any good candidates for Dyson spheres yet?
Yeah, good question about Dyson spheres. We don't. I don't know if anyone has gotten time on Webb to do that. You have to apply for time, so they'd have to make a good case for looking for Dyson spheres. And I can tell you from the scientific community that even though I think it would be interesting, I don't know if they would get time on James Webb to do that. And a lot of this is called, it's like a fishing expedition. A lot of it is we're not sure where it is, let's look here, let's listen and hope to find a signal. So unfortunately for SETI, they get a bad rap a little bit because it's not hypothesis driven. You can't disprove it. We can never disprove that there's no life out there. And you can't disprove that there's no Dyson sphere. So it's not a hypothesis driven type of study. So I don't know of any. I'm sure Webb could do it because it's infrared heat. But I don't know. But I will tell you there's a paper, There's a paper by Ben Zuckerman, and it's open source at this point. It's pretty short. It's on Dyson spheres and how you could measure, he's an astronomer at UCLA, how you could know you're observing a Dyson sphere. So anyone can look it up.
Thank you.
That would be good.
Dyson sphere.
Sorry.
That's okay. Let's see, we'll go to this side.
Thank you for the great talk. Can you figure out where meteorites have come from? And the particular ones with all these interesting amino acids, can you trace back where they might have originated?
Yeah, so that's a great question. So meteorites come from the asteroid belt, most of them. And most of them, we don't know which asteroid. There have been some hypotheses, like for Tarda, there was a recent paper that it could come from far out in the asteroid belt called a D-type asteroid. They try to match up, oh, thank you so much. They try to match up with spectroscopy to try to, when you get the meteorite, you can do measurements on it to try to see if they're similar to other asteroids that have been analyzed. There are a few that we know for sure. So there's a group of meteorites, the HEDs, Howardites, Eucrites, Diogenites, that come from Vesta family asteroids. So those are unusual. Those are usually valuable in that we know exactly which asteroid family. Then Mars and the Moon. We have meteorites from the Mars and the Moon. And we know those are from Mars and the Moon for sure, based on all the work done on Mars. And of course, we have the Apollo rocks to compare to those meteorites from the Moon. The rest of them are really asteroidal. The amino acids, so Tarda, they think might come from D-type asteroids, so that's getting more specific. But beyond that, it's very hard to do because there's so many asteroids out there that they can kind of categorize them a little bit. But they look at the composition, so like Mars, the composition of the chemistry is preserved from the atmosphere. So that's how you know your meteorites from Mars. For the Moon, it's similar, that the composition of elements is very much like the Apollo rocks. And so they can tell which part, Maria or other parts of the Moon, and but they know that's lunar. And so those are the only real categories we have. And then the irons are from some core of some failed planet. So these are fun. These are from a larger body that broke up, and then we get the iron. The pure iron comes to Earth. And so we don't have any pure iron like this on Earth. So anytime we get an iron that's analyzed, we know that it's got to be meteoritic iron. Yeah, it's the most common one to confuse with Earth rocks, though.
Okay, I think we've got time for one more question, if that's okay.
We have one over here.
Okay.
Go ahead.
Go.
Atmospheric pressure, like saying you're colonizing Mars and what that would
Yeah.
do is change the atmospheric pressure within Mars. Now, what would retain that pressure and
Yeah.
the gases from just going
Right.
into the vastest
Right.
space?
So how to preserve that atmosphere on Mars if we terraform it, we don't know. I mean, the idea, either you continuously pump out the gases, but there's no way to keep that atmosphere without a magnetic field. So there has to be either you could create your own dynamo effect.
The vacuum of space versus the positive pressure system that we're
No, it's the solar wind. So the solar wind is coming and stripping off the atmosphere, and we have a magnetic field on Earth. And I could, if I had this data set up, I'd show you in open space. But on Earth, we have a magnetic field because of our spinning iron core. That magnetic field protects us from the solar wind. The solar wind is going through space at the speed of light, and it's going to hit whatever it hits. And what happens is it gets to Mars, and it strips off that upper atmosphere because there's nothing to stop it. There's no barrier. And so that is the problem, and that's certainly an issue with sending astronauts to Mars and also to the Moon. They don't have the protection of the magnetic field. So, but they're not radiated as much as if we send astronauts to Mars. So there is no way to hold on to it. There are ideas about creating a dynamo, if you could spin Mars. I mean, this is advanced technology that we don't even have. But you'd have to you have to figure out some way to generate a magnetic field. And we don't have, it's like this planetary, planetary civilization. If we're planetary, maybe we could figure that out. That we harness all the elements of our planet and be able to really control the planet, and then you could maybe spin a planet. I mean, that's maybe possible. But there are all these other ways. I mean, creating an atmosphere, some people have thought about smashing an asteroid with ammonia into Mars, but we're good at smashing things into things and blowing things up. But that's not controlled, and that's also not sustainable. So I'm not sure, these are very far future ideas. Okay. And I'll stay up a little bit if you want to ask me.
So when you were showing the intergalactic clusters, why was it in like that?
Oh, yeah. Yeah, that's because we have a blind spot. It's because it's just like in your car, because we exist in a certain place in the universe, and we have a blind spot. And so that's why the Planck data set has those dark cones. And this may seem slow to you, but it's way faster than you could ever travel. So I'm just going to point that out. And so, yeah, that's the Planck data set. And so it just has to do with the fact that we can't see everywhere. And I'll zoom back in again. But I will say one thing that's cool that so here, these cones, that's because we don't have a way to observe these parts of the universe. You could probably fill them in with other galactic clusters, but they're just not, we don't have those observations. But as I zoom out, one thing I didn't do is go all the way out and thinking about what's beyond the universe, what's expanding into, and we don't have an answer for that. We have no definition. So this is the big mystery of cosmology. Are there other universes, other dimensions? We just don't know. It's possible, but we don't know. So anyway. Anyway, I'll sit up here for a few minutes. I know we have to go observing, so my friends here driving are going to pull me out. But if you go to the garden where we're going, I'll be happy to answer more questions. Or as I'm packing up, you can ask me. And if any of the few of you who run up and want a little card about open space, you can take one. But it's also free, so it just takes you to the website openspaceproject.com, and you can download it and have fun. So thanks, everybody. Okay. I want to touch your rock. Yeah, here you go.